I'm happy to introduce our speaker, Gunnar Schaefer. Gunnar is co-founder and chief technology officer of Flywheel. He started working on medical imaging data management at Stanford University in 2010, where he supported the setup and operation of a neuroscience MRI facility that's called the CNI. Based on his work at Stanford, he founded Flywheel in 2015 with a commitment to openness and supporting reproducible research. Today, Gunnar will be covering how Flywheel streamlines data curation and machine learning development. Gunnar?
Thank you for the introduction, Esther. Let me get this going. Here we go. So as Esther said, I'll be talking about data curation and machine learning today as we've envisioned it in the Flywheel platform. And thank you everyone for coming to this webinar to learn more about Flywheel. So for those of you who are not familiar, Flywheel is an informatics platform for biomedical research. We have our origins, as Esther described, in MRI imaging, but the platform is capable of handling imaging data of all types and also non-imaging data of various kinds, such as EEG, for instance, or any kind of tabular data. And the platform supports the entire data lifecycle, so all the way from data acquisition directly at the modalities, all the way through to publication. In doing so, we focus on 4 key areas. We start by capturing data either directly from imaging modalities in case of pure research contexts, or in more clinical settings, we would get the data from PACS systems. And this can either be pushed into Flywheel or pulled out by Flywheel. And the same is true for any kind of non-imaging data, which we can do by monitoring file systems. So it's truly a multimodality system. And one key component of data ingest, of data capture, is de-identification. And for Flywheel, this always happens at the origin. So even when Flywheel is deployed in the cloud, the de-identification happens on premises before the data are ever uploaded into the cloud. And that's, of course, a key security feature. And after that moment, from that moment on, the data are always encrypted, both at transport and at rest. After the initial capture, we move into the curation phase, where we extract metadata from data. So what we call data are the complex objects, the images or the EEG time series. And then any kind of information about those data or about the subject of those that's represented by those data is what we call metadata. And extracting all of that and bringing it into our database and making it accessible through our APIs and through search is the key part of curation. We also we actually kind of leap ahead and use our computation framework to apply automated classification to data. And I'll show you what that looks like in the product in just a moment. For the computation specifically, we have developed a system that allows for elastic scaling of prepackaged compute modules that we call gears. Those gears are actually standard compliant Linux containers, and they can be installed by the end users into the platform. We also provide a number of these ourselves, and they can be simple things like a DICOM to NIFTY conversion or a free surface segmentation, or they can be full-on data analysis pipelines, including project level statistical analyses. And the collaboration feature transcends all of these aspects, allowing you to share your data, to manage permissions yourself, and also sharing the computational modules. And with all of that together, we then enable the imaging research and now increasingly machine learning applications. So the use cases range from academia to clinical research into commercial pharmaceutical research. And specifically in academia, one of our founding sites and the biggest footprint is core facilities. Dedicated research facilities where a lot of NIH-funded projects happen. Sometimes these research facilities get together into multi-center studies where data are recorded or collected at multiple sites and then processed by a centralized site. And Flywheel is a great system for that due to the flexibility of ingesting data either automatically or even through the web interface, and then bringing it all into a central location for quality control and analysis. In clinical settings, it's about scaling research on the clinical data, enabling partnerships, and doing all that while working with the privacy and security risk teams of those customers. In commercial, it's largely, our engagements are largely around AI and personalized healthcare, examining data from clinical trials, and overall increasing pharma efficiency. And we do all this in an extremely open way. As Esther introduced, being open is really a founding principle, as is reproducibility. And Flywheel has adhered to those principles over the years. So all of our APIs are open. When you'll see some screenshots of the web interface sits cleanly on top of our open APIs. We also provide SDKs for various programming languages, and those things combined make the platform extremely extensible and able to integrate with other systems. So for instance, integrating with REDCap, where questionnaires are captured, is a common thing for our customers even to do on their own. We're happy to help, but they don't necessarily need our help. And we're also committed to open source. So all the tooling that will run on a user's own computer, so for instance, our command line interface or the mentioned SDKs here are all open source. In terms of sharing and reuse, we support both data sharing as well as algorithm sharing. And we've also implemented comprehensive bid support. So not only can you upload your own bids data into Flywheel and manage it there, but we also have extensive functionality for curating data that is not in bits format yet, that was just acquired, and bringing it into bits format for sharing in that consistent format. And we actually have had a webinar on this that you'll be able to find on our website as well. Finally, reproducibility. We try to build as much reproducible components as possible. So the gears that we provide and the entire framework around it, the automated provenance capture, all aid in the reproducibility. And our Chief Product Officer, Travis Richardson, actually gave a webinar, the first webinar on open science in Flywheel. That's the one Esther referred to earlier. So today we want to talk about data curation and machine learning. So the state of the affairs here is a little bit bleak. Several studies have found that about 80% of data scientists' time is spent finding, cleansing, and organizing data, and leaving only 20% to actually perform the analysis. And we don't think that's right. And we try to put our tooling into effect in order to shift that ratio, ideally reversing it, spending 20% getting your data ready and spending 80% of your time doing the interesting science part. So let's try to understand what's going on here. So machine learning, there's kind of a life cycle of that the data go through, and this might even repeat as you're retraining your models over and over again. So typically it starts with finding data. You need to get your hands on some useful data. And then you got to make sure that you have the right kind of consistency and quality of your data. Finally, you have to move into labeling, either manual or automated labeling, and any kind of additional annotation you need to do before you then get to the last 20%, the training and scoring of your model. So the common problems there are that your data are not ready. They're not properly organized or labeled, and they're not uniformly quality controlled. With that, you also have increasing scale. So the resolution, both spatial and temporal resolution of instruments, continue to get better. Multimodality studies are extremely common, and getting data from multiple sources is also common. So scale is going up. At the same time, your privacy and compliance requirements are going up. So people are getting quite serious these days about that. And so a lot of people are in a space where they're no longer comfortable doing what used to be okay some time ago. So with that said, generally the needs are that users need good search to get started with the right data sets. They have to run automated quality controls to get to that right standard. And then they want to apply standardized pre-processing, followed by automated and manual labeling. And in doing all of that, provenance tracking, so you know how your data got to where you have them. Okay, so let's get started with looking at how data curation works in Flywheel. The first step here is automated labeling. And we have our Gears framework to help with that. And you can see in the top left screenshot, the blue box, we've applied a classification system to these MR data. So both the modality as well as the modality subtype have been set here in both a human readable as well as a machine readable structure. And as I mentioned before, we actually use our computational framework to carry out this classification. And you can see the reference to the classification gear at the bottom. And then at the top right, you can see the rule that launches this classification in an automated fashion. So this rule is quite simple. It merely says that if the file type is DICOM, then run this MR classifier. And these rules can be configured on a project by project basis, so you can have entirely different things going on in different projects. Another rule that we typically set our customers up with is that if the file type is DICOM and the classification has been set, so it's non-empty, then run DICOM to NIFTY conversion. And then finally, another rule might be that if the file type is NIFTY and it is a structural or functional scan, then run MRI-QC. So this is how the sort of the base setup of a neuroscience project would look like. And the rules are declarative, meaning you don't specify them in a certain order. You just specify condition and what needs to happen in that condition. So with the rules I just described, even if a NIFTY was uploaded manually and then the classification was set on it manually, the rule would still fire off and kick off the MRI-QC process. Now, after the initial classification, you might want to start drawing some ROIs and annotating your data manually, and you might have a team to do that. And in order to support that, we have a built-in radiology-grade viewer, and it supports multi-user annotations, as you can see with the little avatars in the screenshot. And when you draw an ROI, you have different options for different kinds of ROIs you want to draw, but you also have this customizable menu that pops up for how to label your data. And this is quite important. You might have a labeling team and you want to ensure that they consistently apply these labels and not type something new every time they see it. So you on your project, you can configure what this menu should look like, and from then on, the labeling will be extremely consistent. In the bottom screenshot, you can see we've taken it even a step further. There's a little form in the bottom right that the reader has to fill out. Those radio buttons have to be selected before they can mark the study as completed. So this is really guides the reader, whom often a radiologist, not so computer savvy, through this process very efficiently. So in doing those things and doing them consistently, and the consistency is supported by the system, you make your data fair. This is something that the NIH has proposed some years ago, and Flywheel has adopted this model to help people share their data and reuse it. So fair means your data are findable, accessible, interoperable, and reusable. I'm not going to go into the details here, but this is sort of a side effect that you get by managing your data in Flywheel. Okay, so now that we've done this, we've classified our data, we've labeled our data, we can explore some new research questions. So the sample question here is, find all images, treatments, and outcomes for patients with a glioblastoma larger than n millimeters in size. And then train a machine learning model to optimize the treatment. So how can we do that? So the next thing we need to use is Flywheel's search functionality. And we have two different kinds of search. The simpler kind works with auto-generated facets. So those are these groups of checkboxes that you see. You've probably seen this on shopping websites when you buy a TV, and you can you have checkboxes for the brand and for the screen size and different things. Those are actually auto-generated. And we do the same thing here for research data. So file types are automatically extracted, and modalities are extracted, and so on. And so you can do quite a bit of this query by simply using your mouse and checking a few boxes. We also then have an advanced search, which allows you to freeform type in your own query in a SQL-like fashion. We call that FlyQL, and you can see the sample of that on the screen there in the blue box. In the advanced search, you can also save your queries and retrieve and rerun them later. Okay, so we're through the data curation part. Now we're on into machine learning. So this is sort of a general overview of what machine learning looks like in Flywheel. Again, we start with ingesting data from various sources. So you might be getting data from your clinical systems or even from partners. We've also integrated with Google's healthcare API as an example, and there might be supplemental reports. So this might be EMR data, or again, in research context, often some kind of electronic data capture such as REDCap. You bring your data all into Flywheel, you prepare the training data as we've discussed, and now you're on to the actual training. And due to, through Flywheel's open APIs and our extensibility, you're free to use the machine learning tools of your choice. We're committed to giving our users as much freedom as possible and not any kind of lock-in. So we're not going to force you to run your training directly in the platform. You're welcome to use the different SDKs. So our Python SDK is very useful in TensorFlow and PyTorch type of contexts. You can use your own hardware to carry out the training, but you can also use cloud training environments such as Google's CloudML or the AutoML Vision API. And the reason I mention those is because we've actually been playing with that and built a prototype for the AutoML Vision API to classify MRI data. And I'll point to that in this example here. So the way we've gone about this is that we built a gear that gets data from Flywheel along with the classification that we have for those data. So we just did T1 and T2 scans for this example. And it uploads all of that data to Google's AutoML environment along with those labels. It then kicks off the training. So the user doesn't ever have to look at the AutoML interface here. They just are in the Flywheel environment and they're running the gear. And the gear will do this. And then after the training completes, the resulting model is actually automatically deployed in Google's environment. It becomes available as yet another gear in the Flywheel system to use the AI that you just created. And for our simple example, with just a few data sets here, we were able to classify T1 versus T2 without ever writing any machine learning code. Okay, so in conclusion, Flywheel has very robust support for the machine learning lifecycle. So this is back at where we started. We're able to find useful data either through directly interrogating the data hierarchy in Flywheel. We have the classification and the search to support us in doing those things. we're able to very easily apply quality and consistency. So there's a little screenshot of MRI-QC actually here, and we're able to do those processes automatically through our rules system. There's also, I didn't mention this before, there's also templates for what data should look like. So a given DICOM study should have certain components that can be specified in session templates, and you would have those sessions flagged if they're incomplete. We looked at how users can apply manual labeling. They can draw ROIs and annotate them that way. Finally, I alluded to how the training would actually be done, then either through Gears integrating with the cloud platforms, or using the standard methodologies of PyTorch and TensorFlow, and in combination with our Python SDK. Okay, that's all I wanted to share today. Thanks for your attention, and happy to take your questions now.
Yes, feel free to submit your questions in the Q&A feature of Zoom, or if you'd like to raise your hand, you may ask a question live over audio. We'll wait a few minutes for you to submit your questions. Our first question is, are there any gears that facilitate debugging? From Ozan Genç.
Yeah, so the gears, I don't quite understand the question. The gears can be debugged. There's no gear that does the debugging for you. So the way it works when you run a gear, you can develop it actually locally. Part of our command line interface includes a gear builder functionality, and you're able to also then run the gear locally against local data. When you run it, after you've installed it into the Flywheel platform, you're able to get the logs, standard error and standard out of the gear run in real time. So those are the debugging tools that we present to you. If it's a kind of a algorithmic issue, then the local debugging, you can use your standard tools for that is probably the way to go. The final Flywheel integration step, usually the logs are sufficient to do that. If you follow the gear specification, then the problem we see some users run into more frequently is that the allotted machine that the gear gets executed on doesn't have enough memory, and so reading the error message will explain that, and then you can work with us to make sure your gear runs on a bigger machine.
So thank you all so much for attending. I invite you to attend our exhibitor hours following the conclusion of this webinar, and to visit our website or email info@flywheel.io with any questions.